Well, so now today, first I will discuss the LTI controllability, and then we will discuss some principle of our observability, and then eventually at the end we will discuss some control problems. So first, LTI controllability, the linear time invariant. We all know by this time that for linear time invariant system, the system matrix become independent of our time. Now it is controllable if and only if the n cross uh, n cross nm controllability matrix that satisfies b a b square b, this matrix must have a rank is equal to n. Now we prove that rank condition uh, in this 2 will fail if the system is not controllable. And furthermore, what we can show that for linear controllability, what we studied here, if this rank fails, then uh, that will always imply the rank of the controllability Gramian, or means the Gramian matrix will not be invertible. If the rank condition fails, then what can you expect for the Gramian? If rank condition fails, then there exists a non-zero n cross 1 vector xa such that what you can write xat transpose akp is equal to 0. If rank condition satisfies, then you will get this one, like this theorem holds good. But if rank condition fails, then obviously for a value of k, you will have, for a particular xa, you will have akb is equal to 0, right? Now think about one simple uh, understanding, that this, don't you think that this implies if we go to our previous chapter when we'll discuss solution of linear system, and from that can't we say that this one is equal to this means formula that x a transpose w t naught comma a is equal to summation running from t naught to t a, this phi t comma a we can replace. What is your w? Yes, this one can't we replace this one by this whole thing, and if we can replace it by this structure, then this is becoming 0, and therefore it implies that our w t naught comma tf is not invertible. Now conversely, what we can see, that if the Gramian is not invertible, then there exists a non-zero xa such that we will have this Gramian is equal to 0, right? Now if that is the case, then what we will have? We will have that xa, like exactly what we did for the first theorem of our last video, that is video number 17, last first theorem. If you consider, then how we proceeded means we did it, we just find out an existence of a non-zero. Like if the Gramian is not invertible, then it will give us this, and from that it simply implies, if you apply the first theorem of our last video, you will see that it boils down to this condition for that interval period. At t is equal to t naught, you will obtain x transpose b is equal to 0, and then if you differentiate it k times, what you will get? If you differentiate it k times, then you will get it like minus 1 to the power k x transpose akb is equal to 0, for k is equal to 0 to n minus 1. Therefore, the total things is becoming x transpose b ab a to the power n minus b is equal to 0. Right? And thereby it proves that our rank condition is not sufficient, means it fails to comply with our requirement. Now we will go to the observability part. What does it mean when I will solve a few problems? You will get it. Actually, there is a means confusion, and many people loves to discuss forms that are typically related to this controllability form, like how to convert a system in controllable canonical form, this that. But in my opinion, what I will do, I will follow approach of some other books, and I will do it at the end where we will try to realize a system, try to design a system. Because now we are just trying to do analysis. For analysis purpose, yes, one kind of analysis can be done for this system, but that is very preliminary, known as Gilbert Analysis. In one day during class discussion, I will discuss it. It is just simple linearizing and then checking the entries. Actually, it is means there are thousands, many more tests available for controllability. We can have Popov-Belfich Hottest test, PBH test for controllability. Those things, if I get some time, then I will discuss. But the basic essence of controllability, what can be discussed, means for undergraduate level, that I have already covered. Okay, so in observability, again we can have a similar kind of discussion to understand the physical meaning of an observable system. Before I go further, I would like to give you that description, that same kind of discussion we can do for observable system that we have done for controllable system also. Like we can have a system. Suppose this is your output terminal, and here you are connecting one capacitor. So the initial capacitor voltage, you are having some voltage. All our resistance are equal to R. So it will be difficult for you to figure out any voltage across the output terminal, irrespective of whatever value you are having in your capacitor. It will never show you anything. So that is what makes a system unobservable, right? Now here we can write it in that expression wise, that x dot t is equal to at xt, xt naught is equal to x naught, yt is equal to c xt. This whole thing, equation 5 is observable or t naught comma tf if any initial state x t naught is equal to x naught is uniquely determined by the corresponding response yt for t within that time span. And it is like the controllable system, it is also if you are considering a time varying system, then your system are going to be observable. We can only guarantee within that closed interval t naught to tf. We do not know how the system would behave if we allow it to exceed and go beyond tf. Like if your t greater than tf, then how your system will start behaving, that we do not have any idea about that, right? So this is a very important point that we must not overlook or forget. Now that this theorem, we are going to present one theorem like this on based on observability, like same kind of Brownian kind of things we are going to construct. Like equation 5, the linear state equation 5 is observable on that closed interval. If and only if the n cross n matrix M T naught comma Tf is your this one, the observability Gramian is invertible, right? So how can we prove that one? Let us multiply the solution of both sides of the solution with this let us multiply both sides of this equation by that phi t comma t naught c transpose t, and then let us integrate it. Then what you will get, your right side will become that one what was your Gramian. And do not get confused with the fact that how x naught is coming out of your integration, because x naught is a constant vector. It has nothing to do with your time, because you are mentioning it is t naught to tf, means you are means for a given t naught you will have a different given x naught. And don't get confused it with uniform, non-uniform. It has nothing to do with uniform and non-uniform stability. It is this x naught is only a vector that you can have during time t naught, right? Now from this equation 7, if we can determine the left side yt, that is from like if our m t naught comma tf is invertible, then there exists xa, or means any xa, for any xa we can means uniquely determine the value. And if m t naught comma tf is not invertible, then there exists a non-zero n cross 1 vector for which we can have this condition. Like if it is invertible, as we know that is common for everywhere, that if you are dealing with a system x is equal to b and a is invertible, then for every x you will get means from that equation you can uniquely figure out x. Actually, that is what happened when our number of linear independent equation becomes equal to the number of unknown variables. And when it is not the case, then what you will have? You will have a non-zero n cross 1 vector for which you will have this mt naught comma tf xa is equal to 0. Now, furthermore, if this is the case, then this implies that x, what, where it goes, it implies that if we take transpose, then what we will have? That we will have xa transpose. Let me write. Like this implies we will have xa transpose m t naught comma tf x transpose xa is equal to 0, and that will further yield that c t phi t comma t naught xa is equal to 0 or t for some t belongs to t naught comma tf, not for all t, for some t, because we are not sure that whether m t naught comma tf is always non-invertible or it becomes non-invertible for a particular value of time within that time span. Do note here again and again I am telling you that for time varying system we are only considering system that is within a given span, not throughout the time. So this observability Gramian M is like, it is just as similar as the controllability Gramian W, and they are having several interesting properties like controllability Gramian. What I said, for controllability Gramian, if it is positive, it must be symmetric and positive semi-definite, but unless you are getting a positive definite controllability Gramian, you cannot ensure your system is controllable within that time interval. And the same is true for observability Gramian. It is symmetric and positive semi-definite by its construction, but you must ensure that it is not only symmetric and positive semi-definite, but it is positive definite also, to ensure your system controllability, observability. Now then we again here this means construction of this Gramian and its computation. It's not very easy. So to circumvent the problem, what we did for controllability case with K, we can do here with our L, like we can define like corresponding to equation 5, corresponding to equation 5 and subject to existence and continuity of the derivatives, what we can have, we can define a P cross N matrix function by our L naught T is equal to Ct, and thereafter just like K, only difference is that in case of K it was B, and in case of C, in case of controllability it was B. Means you can see B and C matrix as the window or the passage that either allow your input energy to reach your system core. B can be viewed as that, and you can view your like C matrix as a window using which you can see the inner energy of a system. Means what is there, means state is something that is related to your inner energy. And now obviously means knowing only the energy is not sufficient. You must know that how the energies are related to all the states. So that is also important, that C gives you a window to visualize what is happening inside your system. And if your system is n-dimensional, like suppose you can visualize C, try to be a bit intuitive. You can visualize C, suppose you are having a room. The room is having 4 walls. Now if you have say you are having something happens inside your room, means 3-dimensional object is there. Now inside that room, then you need what? Then you need windows to visualize that object, and the windows must be like, if I place 4 windows on a single if all the windows are placed at a single wall, then it can only give you one-sided view. But if the windows are placed on different walls, the openings are on different walls, then you will get the different side of that object. So that becomes very important. So you must understand that. And although I am talking about a 3-dimensional object, if you can ensure that that 3-dimensional object is means like one side, suppose it is a kind of say quadruped or something, that is having the 2 opposite sides are identical to each other, then visualizing one, you can get idea about the other. So in that way, if you place all the 3 windows on a single wall, you will not get any information about color or that this color of a particular surface of that quadruped. So you need to be very means this C, B, all these are like something through which you can either reach into the system, or you can view what is happening inside the system. Now that suppose we have a queue, so what we are having here, this is the definition. Just we did it in the same way that we defined it for controllability case. Now we are having a theorem. This is a theorem. I'm feeling terribly sick, so that is why I'm not able to deliver my full energy. Suppose Q is a positive integer such that for all t belongs to T0, Tf, Ct is Q times continuously differentiable. Then equation 5 is observable on T0, Tf if, and obviously if you are talking about Ct is Q times differentiable, then you need to write At is if rank of this one constructed using L0 Ta to LQ Ta is equal to, it must be is equal to n. We can prove this theorem exactly using the same method that we did for our previous case, right? And also when you are having a time invariant system, then your AT will become A and CT will become C. Then the equation is observable on T naught comma TA. If we can have this matrix, that is NP cross N observability matrix, that satisfies our requirement of observability. Now another interesting things is that controllability and observability, they are kind of dual to each other. What does mean by that dual is like if we define a state that is get dot t is equal to is controllable only if we have this one is observable. Sorry. The first equation is comparable, means controllable if the second equation, that is written under this dotted line, is observable. Right, now we will discuss a few examples and that will help you to solve worksheet problem. So let us consider. So here, as we can see, that it is clearly a case of a constant matrix A and B, and you can form this matrix like how many rows will be there. There will be B, A, B, oh God. There are 4 states here. How many states we are having? N is equal to 4. So how many it will be having? B, A, B, A square B. But A cube B will not be here. Here we will have only A square B up to this term. Now see that what is happening here. Why like yeah, B, A, B, A square B. Then what we will get, it will give us this B, A, B, A square B. Just a minute. Okay, so here as per our previous conversation, what we can do is that we can have a matrix, like we can construct our controllability matrix M as here, as I have written. this is our controllability matrix for linear time invariant system for LTI, and we need to check that whether this matrix is having full means row rank or not, means whether the rank of this matrix is equal to 4 or it is less than 4. If it is less than 4, then we can conclude that this is not controllable. However, here we can do a little bit manipulation to make our calculation easier. We can show that if we have our columns of B is more than one column, like here you can have two columns in your B matrix, what you can do is that instead of calculating this one, you can do or means can conclude correctly about your system controllability using this one also. Here what we should means, if you ask me to generalize about that how can we calculate, the formula is that if you are having m number of input, then it should be this is the formula that we should use to calculate our means controllability matrix. So please note this one, it may help you while calculating the controllability matrix. Also one thing you can do is that means we can go for Gilbert transformation. What is that Gilbert method? In Gilbert method, what we do, we just try to obtain a diagonalized matrix form. So if it is diagonalized, let me show you just an example, small example I'm telling you, that in Gilbert form, what we do, first we convert it AD, that is using state transformation, where A was your original state matrix. So here what you will see that in your new coordinate, that is in diagonal form, your AD is like, or let me write it in terms of ZD dot. Just a minute, let me write, because my system is creating a hell lot of problems. This is known as Gilbert method. In Gilbert method, what we do, we first diagonalize one and see what is the essence of diagonalization. You can also consider it as decoupled state transformation. I'll discuss different type of state transformation later in detail, but the essence of this decoupled state transformation is that after having this decoupled form, now you can see that z1 dot, if you write, it will become z1 dot is equal to, so it will only depend on z1 plus, now suppose if you want to reach a particular value of z1 for a given system, in that case it is not possible for you, if this b1 becomes 0, then it will become completely uncontrollable. So the essence of Gilbert method is that it tells that first diagonalize and then check the row entries of your B matrix. If a complete row is 0, then your system is uncontrollable. So obviously if you consider this one, it may gives you an impression that this is an uncontrollable system because we are having two rows with complete 0 entries, but it is not the case because our original system matrix is not in decoupled form. You can see that states are linked here, like here you can see that x1 dot is dependent on x2, while x2 is dependent on x1 and x4. Similarly, x3 is dependent on x4 while x4 is dependent on x2, and you are governing the rate of change of x2 and x4. By that it means you are somehow trying to govern that, like the states here in means x2 and x4 will get a direct impact because they are controlled by x2 is controlled by u1 and x4 is being controlled by u4, sorry, u2. You are having two input u1 and u2 because there is two columns, so u1 will govern x2, u2 will govern x4. But using these two you can, because there is no constraint imposed on your input, you can make sure that these x2 and x4 will go to 0, and while they will go to 0 you can clearly see that x1 dot is dependent on x2. And not only that, like you may ask me a question that if I make x2 is equal to 0, then it may happen that x1 dot becomes 0. Like some variables rate of change is becoming 0 doesn't imply that the variable itself becomes 0. Like if you take ddt of any constant, it will give you 0, but that doesn't mean the constant is itself is equal to 0. So here lies the answer, that the dependence of x2 on x1. So as long as you are not making x1 is equal to 0, then due to the presence of x1 here, x2 will again become non-zero, and then again it will cause change in your x1. So if you want to keep all of them in origin, then you have to, these control efforts have to drive something, or means be shaped in such a way that they should be able to keep all these states in that origin. Otherwise it is not at all possible for the control input to ensure stability, right? So they are somehow related, and that we can prove, right? And that is what is the essence of Gilbert one, that if after diagonalization it becomes very clear to you, you do not need to analyze that who is dependent on whom and how to figure it out. So you can check the entries and then figure it out, right? Now we'll do some other important things about transfer function pole zero cancellation. But before that, I would like to throw one more important question that was asked about minimal polynomial and characteristics polynomial. So for that, I am taking the example of this matrix. For this matrix, you can see, if you find out the eigenvalues of this matrix are lambda is equal to 2 and lambda is equal to 1. So if you now try to find out, clearly it is having two repetitive eigenvalue at lambda is equal to 2. But there is no harm. But if you, after representing the Jordan eigenform, if you find the Jordan eigenform is not linked, then there is a problem. What is the problem? If you from this, this is the eigenvectors associated with corresponding eigenvalues, and after that if you represent them in this way, you will get that this whole thing, you can see that the determinant is something that is a function of lambda minus 2, right? So here the minimal polynomial is becoming lambda square minus 3 lambda plus 2. However, the characteristics polynomial, obviously it's for three-dimensional matrix, so characteristics polynomial will give you lambda cube minus 5 lambda square plus 8 lambda minus 4. Now I know apparently this makes you very confused and means give you a wrong notion that whenever there is Jordan, then there is a chance that characteristics polynomial and minimal polynomial there will be an order difference, and minimal polynomial will be 1 or degree less than characteristics polynomial depending on the number of repetitive root but that is not the case. Let me show you one simple example on this. Now consider this A matrix. For this A matrix we will get the similar kind of things, like if you do this one, you will find the characteristics equation means will become this. But however, you will be able to realize some change in Jordan canonical form, while instead of 0 you will see that this entry is here is 1, and that will make a clear difference, that instead of having means multiple eigenvalues that are not linked in Jordan chain, which was in the previous case, now you are having a Jordan block or multiple eigenvalues that are linked, right? And then if you see, you can figure out that your characteristics polynomial is equal to minimal polynomial for your given matrix. Okay. Now let us go to our next problem. So in next problem here I would like to show you something that would means this is not that important, but this manipulation, we will find this manipulation quite useful when we will try to prove that if there is a pole zero cancellation, that would lead us to a situation where the system would become an uncontrollable system, or simply stated, for a controllable or observable system, it should not have any pole zero cancellation in its transfer function. So now let us try to first realize this. The claim here is that we have to prove that this Si minus A inverse is equal to j is equal to 0, summation running from 0 to m minus 1 is j, to quite a complicated expression, and you can read it by yourself. I'm not going to read and waste time on this. Where this one, this is your minimal polynomial. It is not characteristics polynomial, rather it is your minimal polynomial. Right? Now this minimal polynomial, let us put that obviously alpha naught is equal to 1 and m is the degree of minimal polynomial, m less than is equal to n. Now solution, we can write p is equal to Si minus A inverse. That means whatever we need to prove, the left side we just assign it with a variable p. So from that p, what we can write, that if we just do some algebra, then it will become Sp is equal to AP plus I. This is not a big deal. You can multiply both sides with Si minus A, pre-multiply both sides with Si minus A, then obviously your left side will become Sp minus AP and right side will become I. Then if you side transpose AP, then you will get this equation. Now pre-multiply again with Si plus A. Previously it was pre-multiplication with Si minus A, now it is pre-multiplication with Si plus A, and that gives us the both side of the equation. And if you do a little bit manipulation from this stage, you will get this one. that a square p is equal to a square p plus a plus si. Similarly, if you proceed and do it in the recursive form, then you will get this. So finally, after completion of this recursive process and continue it till SMP, what you will get that p is equal to p, sp is equal to ap plus I, s square p is equal to s square p plus a plus si, s to the power 3p means s cube p is equal to a cube p plus s square plus sa plus s square I. Then you will see that it gives you at the end SMP is equal to AMP plus AM minus 1 plus SM minus 2 plus SM minus 2A plus SM minus 1I. So where M is the again degree of minimal polynomial A. Now therefore what we can write is that, like if we write this form of equation, we will get m I is equal to 0, m minus 1 aip plus m I is equal to 1 alpha m minus I, here alpha m minus I again, this plus SR 0. Let us put this equation as hash because we will need this hash form of equation. This is not a special equation, but we will use this later to prove that pole zero cancellation. If pole zero cancellation occurs, then the system becomes uncontrollable or unobservable. Now, obviously, we need to note that, like here, this for P, that this alpha m minus I AIP is equal to this. If you want to verify this, you just need to do a little bit manipulation by yourself. Like I can do it, but it will unnecessarily consume at least half an hour for me to just show you the intermediate algebraic steps. It is just simple. If you become a bit mindful and do it properly, you will get the correct form. Then if we cite transpose, we will get this, and eventually we will reach to a conclusion that this is equal to this one, and needless to say, the whatever we are having here is our, this whole thing is like det Si minus A. So what was given, we have proved that. Again, I am telling you this proof is not important, but what we are going to prove, it is very important for that. That any cancellation in transfer function would lead us to an uncontrollable system. Well, so we are ready to understand that pole zero cancellation is not desirable for controllability perspective. Here, for sake of simplicity, we are taking a single input, single output system. Although here we are only dealing with the state equation, but we will because we are dealing with controllability. Now before I proceed, here you can see that I have written only the equation between state and input. So basically I am talking about only the controllability perspective. However, try to understand my question first. When I am talking about pole zero, generally our common notion is that zero is something that is related to output, pole is something that is related to input. So how this zero and pole zero cancellation we could understand even without not knowing the output, or whatever common understanding we developed in our mind was something wrong, or what I said there is a contradiction. If a contradiction exists, then what is that contradiction that we need to figure out? Anyway, so keep it simple. Let us take a single input system, n-dimensional system given by this equation with initial condition is equal to 0, and our goal is to ensure that the system is the necessary and sufficient condition for complete state controllability is that no cancellation occurs in our transfer function matrix. So if we consider our transfer function matrix, then it will become something that is xs is equal to si minus a inverse bus. Here one common thing can come in your mind, that we have also our C means what is our output. What I was trying to mention, that output is ys is equal to c into xs if we consider it's a time invariant system. I am doing this proof for time invariant system for ease of understanding. So if we are talking about transfer function, then transfer function is basically c si minus a inverse b. So how we are supposed to conclude from this only without even considering c? How can we decide that whether any pole zero cancellation is taking place or not? That is very, very important to understand. So you need to figure out that even without considering C, how we can conclude about possible pole zero cancellation just by observing this state xs. I hope my question is clear. Now let us consider the proof. So Si minus A inverse B, we can write it in this way because B is an n-dimensional matrix, and Si minus A inverse, if you consider the adjoint Si minus A, will give you another n-dimensional square matrix, n cross n square matrix. So when you multiply this, BUS is a n-dimensional vector, so that will again give you an n-dimensional vector where each entry of your n-dimensional vectors are polynomial of S, that is written by P1s, P2s, Pns, right? So what we are talking about by means of pole zero cancellation, we are mentioning that if the polynomial P1s and this Si minus A inverse B has no common factor. Once again, that all this polynomial and Si minus A is not having any factor in common. But again, what if we have a transfer function that is like, if our C is something like, let me give you one example. Say among these n polynomials P2 and det Si minus A, these two polynomials, det Si minus A will also give you a polynomial of S, and P2S is also a polynomial of S, and let us consider only P2S and Si minus A are having two means these are the having common factors. Now if these are having common factors, and suppose my C matrix is like 1 or row matrix 1 or row vector 1 and rest of the entries 0. So eventually your transfer function will become P1s by det Si minus A. Now in that case there is no pole zero cancellation, or is there any chance of pole zero cancellation? That we need to figure out. Like in case a pole zero cancellation takes place between P2s and det Si minus A, does it imply that pole zero cancellation will take place for all other polynomial, or it is only specific for P2S? Anyway, I am here just to show you the mathematical manipulation. Rest depends on you and you need to figure it out. So what we need to prove, that we need to prove first that pole zero cancellation is only possible if the controllability matrix rank is less than n. So we defined phi si minus a inverse b. Then from previous problem we figure it out that si minus a inverse b can be written like this, right? Now we define a vector Vj that is defined in this way. So basically the goal of defining this vector is to like taking control of your this part we are defining as Vj, and thereby phi is becoming this one. And cancellation means what? Cancellation means if your cancellation occurs, then basically we are saying that these and these are having, means these are having a common factor. So if that is the case, here I made a mistake. It is not n, it should be n minus 1. Yeah. Yes, n minus 1, right. So that will give us, now where sk is a particular eigenvalue for which, eigenvalue means pole, for which the pole zero cancellation takes place. So what we are getting, that V0 is equal to minus sk W0, then V1 is equal to W0 minus sk W1, V2 is equal to W1 minus sk W2. Just we are putting the values and of j is equal to 0 and finding out the corresponding value from here, right? So by equating the coefficients. Now accordingly, if you proceed, you will get an equation that is this one. Now from this equation you will see that this equation finally boils down to an equation where you can write it like this one, the way we put our bracket. Then they can be written like, if you go back to the definition of Vj, then Vj, from the definition of Vj you can figure out that what it was. Like once again I would like to go back to the definition of Vj. Vj is what? That is equal to I is equal to 1 plus j and all this. So if that is the case, then Vj, here you are having all these values and gradually you will get these values. Only goal is that here we want to keep this sk, so we can utilize them as per our means we can take them common. So once we write them in this form, what we figure out that this whole thing becomes this one, right? But don't get confused with this C0 to Cn minus 1 with the entries of C matrix. No way. These C are the coefficient of the polynomial clearly defined by this equation. It has nothing to do with your capital C polynomial. Capital C is your observation matrix. It has nothing to do with that. It is just for sake of or ease of representation. We are just representing this first two terms of this summation by this C naught. Similarly, this is becoming. So basically what we are getting here, the whole thing is becoming a polynomial of Sk. Now, so it is clear that if this becomes 0, then for what is this implies, like what is b, a square b, a n minus 1b, they are the column of your controllability matrix. Now, if these columns are not independent of each other, then you will find out this equation holds good for sum of Ci not is equal to 0. If it is linearly independent, then all the Ci need to be 0. That all the Ci must be equal to 0. But in this case, all the Ci are not is equal to 0. And thereby it implies that the columns are not linearly independent. And therefore, it indicates the rank of your controllability matrix is less than 1. Means less than n. Now, we'll do the counter proof. How to do the counter proof? That we will assume that controllability matrix rank is less than n, and then we will show that it implies a cancellation in our that Si minus A inverse B. So here, in order to show that, what we can do is that again we just expressed in same form. Instead of C, now we use gamma naught, gamma 1, all these things, just slightly different from that, and they give us what they gives us, that as it is like, well, and again b is equal to b can be written as Si minus A into phi. Now we have this holds good. Right? Like Si minus A phi is like we just take Si minus A out of this equation. Now for S, for some S, if Si minus A is not is equal to 0, then it implies that this is equal to 0. Now if this is equal to 0, then we can again do that kind of previous the way we proceed, like phi is equal to phi, A phi is equal to S phi minus B square phi, and finally we obtain that this is equal to, you can see it is just a very simple mathematical manipulation, that it is equal to 0. Now if this becomes 0, then this whole thing, gamma Si phi, will take this form, this expression, right? And then finally, if you do a further manipulation, what you will get the manipulation on the right side, you will get that this I is equal to 1 can one further manipulation is possible, like by considering one additional variable j is equal to 0 and I is equal to j plus 1, and then the whole thing becomes or is taking this shape. Now once this is taking this shape, it implies what? It is implying that phi is equal to, if you consider the previous problem solution, you will find that phi was something, here it was n minus 1 j is equal to 0 sj, and remaining thing was there, and in the denominator it was n summation, it was uh, 0 to n, right? But here you can clearly see that now your phi, let me write the expression of phi, otherwise we will not be able to get it. Yeah, this one. So this one clearly indicates that there is a cancellation. If there is any the controllability matrix is not rank independent, then there is a cancellation in our phi matrix, means phi expression of phi. So hence it means gives us the complete group. But you need to figure out that whether we need to consider C, or even without considering C, we can draw this conclusion.